My name is Matthew, and today I'll be presenting my work on transfer learning and deep reinforcement learning. The main motivation for this project is to evaluate naive neural network transfer as a transfer method in deep reinforcement learning agents to help speed up learning and performance. The main work that I performed in this project was pre-train various reinforcement learning algorithms on one task, then transfer the pre-trained agent to evaluate the speed up in learning and performance on different configurations of that one task. So different configurations of that one task include playing around with the parameters of the environment. For example, since I was working with the cart pull environment, changes to the environment include changes to the mass of the cart, to the pole, to the length of the cart, and the length of the pole. All of these changes make up a new task. So essentially we're seeing how robust are the pre-trained agents to changes in the environment. The three different algorithms that I worked with are the Deep Q network, Monte Carlo policy gradient, and deep deterministic policy gradient algorithms. I chose these three algorithms because they're all deep reinforcement learning algorithms, but as well because one of them is a state value based, another is policy gradient based, and the third one is an actor-critic algorithm meant for continuous action space. Finally, the two environments that I tested transfer learning on are the cart pull and lunar lander environments. So in the cart pull environment, the agent is tasked with balancing a pole on top of a moving cart. With the lunar lander environment, the agent is tasked with safely landing a spaceship. One of our more interesting results is that we saw that pre-trained DQN and DDPG agents have trouble maintaining their optimal behavior when transferred to new tasks. For example, with a cart pull environment, we can see that the DQN pre-trained agent initially has successfully transferred to the new task. However, after roughly 1,000 episodes of training, or longer periods of training, it's outperformed by the randomly initialized agent, as shown in all of these 5 different plots. For the same cart pull environment, we can see that the pre-trained DDPG agent, although at times can achieve the optimal reward of 200, fluctuates significantly during longer periods of training. Additionally, we can see that in 4 out of the 5 tasks, closer to the end of training, the pre-trained agent is outperformed by the randomly initialized agent. However, we did see that the reinforced agent outperforms DQN and DDPG in neural network transfer effectiveness. More clearly, as we can see in these 5 different plots for the same cart pull environment, we can see that the pre-trained reinforced agent successfully transfers to the new task by performing the optimal behavior very early on in training, as well as maintaining the optimal behavior across training, effectively outperforming the randomly initialized agent. To conclude, we believe that our work may suggest that when using naive neural network transfer, it may be more effective to use policy gradient methods as opposed to state value-based algorithms.